This problem looks innocent. Concatenate binary numbers from 1 to n. Sounds like string manipulation, right? That's exactly where most candidates go wrong. Because if you build the actual string, you'll get destroyed by constraints. This problem is a bit-shifting pattern recognition filter. And yes, this is where many candidates get filtered. Let's break it down properly. We're given an integer n. We must 1.2.3 all the way to n. Convert each to binary. Concatenate them. Return the decimal value modulo 10 to the power 9 plus 7. Example. If n equals 3. Binary. 1 becomes 1.2 becomes 1 0.3 becomes 1 1. Concatenated. 1 1 0 1 1. Decimal. 27. Hidden signals in the constraints. N less than or equal to 100,000. Result can be extremely large. Modulo required. That means we are not building strings. We are building a number using bit operations. That's the shift. Let's simulate small n equals 4. We build step by step. Start. Result equals 0. Add 1. Binary length of 1 equals 1. Shift result left by 1. Add 1. 0 shifted left by 1 equals 0. 0 plus 1 equals 1. Now result equals 1. Add 2. Binary length of 2 equals 2. Shift left by 2. 1 shifted left by 2 equals 1 0 0. Add 2. 1 0 0 plus 1 0 equals 1 1 0. Now result equals 6. Add 3. Binary length equals 2. 1 1 0 shifted left by 2 equals 1 1 0 0 0. 1 1 0 0 0 plus 1 1 equals 1 1 0 1 1. Equals 27. Wait, we're not concatenating strings. We're shifting and adding. Let that sink in. Brute force. Why it fails. Naive idea. Binary string plus equals bin of I. Then convert to integer. Problems. The string grows huge. O of n squared bits. Conversion is expensive. Memory heavy. Time complexity becomes unacceptable. This won't pass large test cases. Optimized approach. Bit manipulation. Key idea. When appending the binary of I, we shift the current result left by the number of bits in I. Then we add I. Mathematically, result equals result shifted left by bit length, or I. Why does or work? Because shifting creates empty 0 bits at the end. Adding or ORING produces the same effect. How do we find bit length efficiently? Python gives us I.bit length. But here's the deeper pattern. Bit length increases only when I is a power of 2. Binary lengths change at 1, 2, 4, 8, 16, and so on. So instead of calling bit length every time, we track it. When I and I minus 1 equals 0, power of 2 detected. Bit length increments. That's a classic trick. Here's the Python solution. Define a class solution with a method concatenated binary taking n as input. Set modulo equals 10 to the 9 plus 7. Initialize result to 0 and bit length to 0. Loop I from 1 to n inclusive. Check if I is a power of 2 using I and I minus 1 equals 0. If so, increment bit length by 1. Shift result left by bit length and or with I. Apply modulo to keep the number within bounds. Continue until the loop ends. Return the final result. Optimized. Constant space. Linear time. No strings. Here's the Python solution. Define a class solution with a method concatenated binary taking n as input. Set modulo equals 10 to the 9 plus 7. Initialize result to 0 and bit length to 0. Loop I from 1 to n inclusive. Check if I is a power of 2 using I and I minus 1 equals 0. If so, increment bit length by 1. Shift result left by bit length and or with I. Apply modulo to keep the number within bounds. Continue until the loop ends. Return the final result. Optimized. Constant space. Linear time. No strings. Code breakdown. Interview clarity mode. Step 1. Bit length. We increase it only when hitting a power of 2. Why? Because binary representation grows by 1 bit at those points. Efficient. Elegant. Step 2. I and I minus 1 equals 0. Classic trick. Removes the lowest set bit. If the result is 0, only one bit existed. Power of 2 detection. Interview gold. Step 3. Shifting logic. Result equals open parentheses result shifted left by bit length or I close parentheses modulo mod. Shift left to create space. Or to append bits. Mod to prevent overflow. Why do interviewers love this problem? Tests. Bit manipulation fundamentals. Power of 2 recognition. Overflow control. Modular arithmetic. Pattern detection. Common follow-ups. What if n equals 10 to the 7? Can we remove modulo? Can we derive a formula? Can we parallelize? How to present solution confidently. Step 1. Mention brute force string idea. Step 2. Explain why it fails. Step 3. Shift perspective to bit shifting. Step 4. Derive formula live. Structured thinking wins interviews. The insight here was simple but powerful. Appending binary equals shifting plus adding. That transformation from string thinking to bit thinking is what levels you up. This isn't just a medium problem. It's a pattern builder. If this clicked, you're leveling up. See you in the next one.